I was standing outside the other night late. The neighborhood was completely quiet. The streetlights were humming, and I stopped. I looked up. It was one of those rare, crisp winter nights where the humidity drops and the light pollution seems to pull back just enough to actually see the band of the Milky Way. And I had that feeling, the one, that classic pale blue dot
Well,
feeling.
the Carl Sagan existential crisis, where
Yeah.
you suddenly feel very, very small and the problems of your day just seem, well, ridiculous.
Exactly that. You're standing on this rock orbiting a very average yellow star, which is just one of hundreds of billions in the Milky Way, and you feel insignificant. It's a moment of awe, but it's also a moment of, I don't know,
It
stillness.
is. It's humbling.
But then I started digging into the stack of research we have for today's deep dive, and my perspective didn't just shift, it shattered. Because
Yeah.
even the Milky Way, this thing that feels infinite and eternal to us, it's just one swirling, luminous island in an ocean that is, it's practically unfathomable.
It is a humbling shift in perspective. But here's the thing about that pale blue dot feeling. It's usually serene, isn't it? We look at the night sky and it seems peaceful, static.
Right.
The stars don't move relative to each other in a human lifetime. But what I love about the material we are diving into today is that it completely dismantles that serenity. It takes that postcard image and just rips it in half.
Yes. We look at those photos from Hubble or, the James Webb Space Telescope, those beautiful spirals with the pinks and blues, and they look like paintings. They're majestic, frozen in time. You want to hang them on a wall.
Precisely. But that is an illusion caused by our incredibly short lifespans. If you could live for 1 billion years and watch the sky, you wouldn't see a painting, you would see a demolition derby.
A demolition derby. I like that.
The reality, as our sources today reveal, is so much more chaotic. These are dynamic, violent, living ecosystems. They breathe gas in, they blow it out, they cannibalize their neighbors, and they're constantly being sculpted by invisible forces. The universe isn't a gallery, it's a construction site.
And that is exactly our mission today. We are going to deconstruct the life cycle of a galaxy. We're going to look at how they're built from the ground up, how they die, and this part actually kept me up last night, how our own Milky Way, the galaxy we use as the standard for everything, might actually be a freak of nature.
It's a distinct possibility that we are the odd ones out. I mean, it's entirely plausible we're living in a weird, quiet suburb while the rest of the universe is, living in downtown Manhattan.
We have a massive stack of sources to get through to prove that. We're looking at these hydrodynamical simulations from the University of Memphis and Oxford that model billions of years of cosmic evolution.
Yep.
We have survey data from Stanford regarding our galactic neighbors, the SAGA Survey. And of course, we have to talk about the bodybuilder crisis, those mind-bending images from the James Webb Space Telescope that almost broke cosmology.
It's a heavy stack.
Hmm.
But to make sense of all the chaos, the collisions, the black holes, all the anomalies, we need to start with the architecture. If you want to understand a skyscraper, you don't look at the wallpaper first. You look at the steel girders.
The foundation.
Exactly.
Mm-hmm.
And in the case of galaxies, that frame is what we call the hierarchical clustering model.
Okay, let's unpack this right at the top. Hierarchical clustering, it sounds incredibly technical, almost bureaucratic. But conceptually, is it fair to say it's basically just Legos?
In a sense, yes. That's a great way to put it. It is the theory that the universe was built from the bottom up.
Hmm.
There was a time when we thought maybe giant galaxies formed all at once, sort of a top-down model.
Mm-hmm.
But the evidence just doesn't point that way.
So no instant galaxies.
No. We didn't start with giant, fully formed galaxies immediately after the Big Bang. We started with tiny clumps of matter. These clumps merged to form slightly bigger clumps, which merged again and again and again to create the giants we see today. It's a violent, messy process of accumulation.
So if we are building a galaxy from scratch, if I'm cooking one up in the kitchen and I want to follow this recipe, what actually goes into the pot? What are the ingredients?
Well, you start with the cosmic soup. Immediately after the Big Bang, you have your standard matter, what we call baryonic matter.
Baryonic, that's just the fancy word for normal stuff, right?
Exactly.
Yeah.
That's your protons, neutrons, electrons, the stuff you and I are made of, the stuff stars are made of. But if that was all you had, you'd never get a galaxy. The gravity of just that gas isn't enough to hold it together against the expansion of the universe.
It would just drift apart.
It would. So the most important ingredient is the one you can't see, dark matter.
The invisible scaffold.
Correct. Think of a galaxy like an iceberg. It's the stars, the gas, the planets, everything we can see with our telescopes. That is just the tiny tip of the iceberg poking above the water.
Just the tip.
But underneath, holding it all up, is a massive invisible sphere called a dark matter halo.
I want to pause on that image because it's so contrary to how we experience the world. We're used to what you see is what you get. But you're saying the visible galaxy is basically just decoration on a dark matter structure.
That's not an exaggeration at all. Without dark matter, the visible universe wouldn't exist as it does today. Gravity's the sculptor, but dark matter is the clay. It provides the gravitational, well, the bowl, if you will, that pulls the normal gas in, allowing it to condense and form stars.
So it creates the divot in space-time that everything else falls into.
A perfect way to put it. Without that extra gravity from the dark matter, the gas would just drift apart. No galaxies, no stars, no us.
But here's the thing that always trips people up, and frankly, it trips me up too. We call it dark matter, but we can't see it, we can't touch it or interact with it. For a long time, we didn't even know it was there. How did we go from ignorance to this is the most important ingredient in the universe? It feels like a leap of faith unless you look at the history.
Oh, it wasn't an overnight discovery. It was a slow, dawning realization that the math just didn't add up. It was broken. And for that, we have to go back to 1939. An astronomer named Horace W. Babcock is studying the Andromeda Galaxy, our nearest giant neighbor.
1939. So we're talking pre-computers, basically. He's probably freezing his tail off in an observatory dome somewhere with, like, photographic plates.
Right, he's doing this the hard way. He's measuring the rotation of the galaxy. Specifically, he's measuring how fast the stars are spinning around the center at different distances. Now, basic physics, Kepler's laws, specifically gives us a very clear prediction here.
Right, let's use the solar system as an analogy. The sun is in the middle. It has most of the mass. Mercury is close, so it has to whip around really fast to stay in orbit.
Super fast.
But Pluto is way out in boonies, so it moves much slower. The further out you go from the central mass, the slower you move. Simple.
Exactly. That is a Keplerian orbit. And that's what we expected for galaxies. Most of the stars and the brightness are in the center in the bulge. So we assume most of the mass was in the center.
Logically, yeah.
Therefore, logic dictates that stars on the outskirts should be moving slowly. But that's not what Babcock found.
He found the opposite.
He found that the mass-to-light ratio was increasing radially. In plain English, the stars on the edge of Andromeda were moving way, way too fast. They were moving at the same speed or even faster than the stars in the middle. The curve didn't drop off, it stayed flat.
Okay, so if I'm spinning a kid on a merry-go-round and I spin it too fast, the kid flies off. Why didn't these stars fly off into deep space?
That is the rotation curve problem. That's the whole mystery. The only thing that keeps a star in orbit is gravity. The faster it moves, the more gravity you need to hold onto it. And the visible stars in Andromeda, the ones glowing, they didn't provide nearly enough gravity to hold on to those fast-moving outer stars.
So there had to be something else there.
There had to be. A massive amount of invisible matter providing the extra gravity to glue the galaxy together.
But knowing there's something there and knowing what it is are two different things. It could have just been, I don't know, dark dust, dead stars, a bunch of loose planets.
And for a long time, those were valid theories. We call them machos, massive, compact halo objects. That was a serious contender.
The machos, I love that.
But then you get the smoking gun. You get the bullet cluster.
The bullet cluster. It sounds like an action movie, but it's actually a crime scene investigation on a galactic scale. Walk us through what happened there and why it ruled out dust or dead stars.
It really is a cosmic crash site. It's beautiful. So you have two massive clusters of galaxies that collided with each other. Now, a cluster is made of three things. The galaxies themselves, which are mostly stars.
Okay.
A huge amount of hot gas floating between the galaxies, which is actually most of the normal matter.
Right.
And, of course, dark matter.
Okay, so two of these swarms smash into each other. What happens to the ingredients?
Well, the stars in the galaxies are so spaced out, they mostly myth each other, like two swarms of bees passing through. They just fly past relatively unharmed.
Okay, they ghost each other.
Pretty much.
Eh.
But the gas clouds are huge. They slam into each other. Friction kicks in. The gas slows down and gets incredibly hot, millions of degrees. It gets stuck in the middle of the collision. It stops.
It's a traffic jam. A huge, hot traffic jam of gas.
Exactly. But, and this is the absolute key, the mass didn't stop. Using gravitational lensing, where we look in how gravity from the cluster bends light from background objects, astronomers mapped where the gravity was in this wreckage.
So they could weigh the whole system.
They could. And the gravity wasn't with the hot gas stuck in the middle. The gravity kept going, passing right through the collision, just like the stars did.
Wait, so the stuff we can see, the hot gas, which is most of the normal matter, is in one place, but the center of gravity is in a completely different place.
Precisely. The dark matter passed through the collision like a ghost. It didn't feel friction. It didn't collide with the gas. It just kept going. This proved, beyond a reasonable doubt, that dark matter is a real substance, totally independent of normal matter. It cannot be gas or dust, because gas and dust would have crashed and stuck in the middle.
That's such a distinct image, the visible matter getting smashed and stuck and the dark matter just gliding through, completely indifferent. So if it's a ghost, what is it made of? In the notes, I see terms like WIMPs and axions.
Those are the leading suspects. WIMPs stands for weakly interacting massive particles. Weakly interacting means they don't touch normal matter or light. Massive means they have gravity. It's all in the name.
And axions.
Axions are another theoretical particle, much lighter. And recently, there's been some renewed interest in primordial black holes, tiny black holes from the very beginning of the universe. The jury is still very much out.
But the notes also mention that whatever it is, it has to be cold. Now again, space is cold, but we aren't talking about temperature here, are we?
Not in the sense of a thermometer, no. In particle physics, hot and cold refer to speed. A hot particle moves at close to the speed of light. A good example is a neutrino.
Okay, so why can't dark matter be hot? Why can't it be made of fast-moving particles?
Because the universe is clumpy. We have galaxies, we have clusters, we have these long filaments connecting them. The cosmic web. If dark matter were hot, zipping around at light speed, it would have just smeared out everywhere. It wouldn't have settled down to form those halos we talked about.
It's too energetic to be captured by gravity.
Exactly. It would just escape.
Yeah.
So to build the structures we see, we need cold dark matter particles that move slowly enough to clump together under gravity and build that essential scaffold.
So we have these cold, invisible, ghostly halos scattered through the universe. And this is where that University of Memphis paper comes in, specifically the simulation called JSAGN2. They did something really fascinating. They compared how gas behaves versus how dark matter behaves in a simulation of a Milky Way-like galaxy.
This study is crucial because it highlights that indifference we talked about with the bullet cluster. In a real galaxy, you have chaos.
Right.
You have supernovae exploding, you have jets from black holes shooting out. These are incredibly violent events that heat up the gas and push it around.
Right.
And in the simulation, you see the gas expanding, getting ejected, moving chaotically. It's a complete mess.
But the dark matter.
It doesn't care. The paper explicitly notes that dark matter particles do not react to electromagnetic forces. They don't heat up. You can blow up 1 million stars, and the dark matter halo just sits there, gravitationally unfazed.
It's the anchor.
It is the gravitational anchor. In their simulations, dark matter comprises about 81% of the halo's mass. Because it doesn't get pushed around by the stellar winds or black hole jets, it preserves the structure of the galaxy.
So even when the visible galaxy is, blowing itself up.
The dark matter halo holds it all together. If dark matter reacted to those explosions the way gas does, galaxies might just blow themselves apart entirely. The only reason we have stable galaxies is because 80% of the matter is immune to the chaos inside.
That is a comforting thought in a way. We have this invisible stabilizer, but now we have to build the visible part. We've got the scaffold, now we need the building. And according to the hierarchical clustering model, we don't just build a house, we smash smaller houses together to make a mansion.
The violent dance.
Yeah, I like that. Let's talk about mergers, because the sources describe this as the primary engine of growth for massive galaxies. It's not a gentle process. It's not like 2 raindrops merging on a window pane.
No, it's cataclysmic. Galaxies are gravitationally bound in groups and clusters. They're constantly falling toward one another. And when they meet, the scale of the forces involved is it's hard to comprehend.
I always picture the antenna galaxies when we talk about this. The notes mention them as a distinct example, and for good reason.
The antennae are the perfect real-world laboratory for this. If you look at an image of NGC 4038 and 4039, you see 2 spiral galaxies that are currently in the process of crashing into each other. But they don't look like spirals anymore, do they?
Not at all. They're a mess. You've got these long, thin streams of stars and gas being flung out into space.
Those are the tidal tails. They're thousands of light years long. That's where the name antenna comes from. It looks like an insect.
It does.
Those tails are the result of gravitational tides ripping the galaxies apart as they pass each other. And in the center, where the gas clouds are colliding, you see these bright pink and blue knots. That's a starburst.
So the collision is squeezing the gas.
Squeezing it so hard that millions of new stars are being born all at once. It's an incredible display of cosmic violence and creation happening at the same time.
But here's the problem with looking at the antenna, or any picture from Hubble. It's a snapshot. We see one frame of a billion-year movie. We don't see the before, and we certainly don't see the after. That Oxford academic paper in our stack was trying to solve this by simulating the whole movie, right?
Exactly. This was a study involving a suite of simulations called SBCPP. Essentially, they took two gas-rich disk galaxies, like the Milky Way, and threw them at each other in a computer over and over again to see how the shape, the morphology changes over time.
And their goal was to answer a practical question, wasn't it? Like, if we look at a weird blob in the distant universe, can we tell where in the merger process it is?
Precisely. And they found there's a timeline of chaos. It's not just crash and done.
It's a whole sequence of events.
A fascinating sequence. It starts with the first pass. The galaxies swing by each other for the first time. This is where you get those dramatic tidal tails like the antenna and a huge initial spike in star formation. Gravity squeezes the gas and the galaxy lights up like a Christmas tree. At this stage, it is very obvious that a crash is happening.
Okay, so far so good. That's what we'd expect. But then comes the tricky part, the blind spot.
The maximal separation. This is wild. After the first pass, the momentum carries the galaxies apart again before gravity can pull them back for the final kill. They swing out like a pendulum.
And during this phase, they look normal.
The simulation showed that they can look surprisingly normal again. The tidal tails might fade or disperse. The star formation settles down. If you took a snapshot then, you might not even realize a massive collision is underway. You might just classify it as a regular, undisturbed galaxy.
That's unnerving for astronomers, isn't it? It means we might be undercounting mergers because they're hiding in plain sight.
It's a major challenge. We rely on disturbed morphology, weird shapes to count mergers in the universe. If they can look normal for a few 100 million years in the middle of the crash, our census of the universe is off. We're missing part of the story.
Okay, so after they drift apart, they get pulled back in.
Right. For the final coalescence, the nuclei merge. Chaos returns. You get another huge burst of star formation, and the shape becomes highly asymmetrical again. The whole thing is a wreck.
The paper also mentioned that not all crashes are the same. It's like a car crash. A fender bender is different from a head-on collision. They compared a prograde merger with a radial merger. Help us visualize the difference.
A prograde merger, which is the SBCPP simulation, is like two cars driving side by side on the highway and swiping into each other. They're both spinning in the same direction relative to their orbit. It's violent, but there is sort of flow to it.
Okay, a sideswipe. What's a radial merger?
A radial merger, the SBCR in the study, is a direct head-on collision.
Ouch.
Indeed. The simulations show that in a head-on collision, the dynamics are completely different.
Wow.
There is almost no time between the first pass and the final merger. The galaxies just slam together.
So no long drawn-out dance.
None. Instead of two distinct bursts of star formation separated by that quiet pause, you just get one massive, messy explosion of activity. It's much more violent, and the whole process completes much faster.
So if you're an observer, a head-on collision might just look like one giant flash, whereas a prograde merger is a long, drawn-out drama with intermissions.
Exactly. And this leads to another really surprising finding in the Oxford paper regarding what comes out the other side, the remnant.
Right. Now, I always thought, and I think this is the common wisdom, that when two spiral galaxies merge, they destroy the delicate spiral structure, and you're left with a boring, red, dead elliptical galaxy, just a big football-shaped blob of old stars.
That has been the standard textbook answer for decades.
Yeah.
Mergers kill spirals and make ellipticals. End of story. But the Oxford simulations found something different, something much more interesting.
What did they find?
If the merger is gas-rich, meaning the two colliding galaxies have plenty of fuel, the remnant isn't always a featureless blob.
It can rebuild. So the spiral can come back.
It can. The gas has angular momentum. It spins. As it cools down after the chaos of the crash, it can settle back into a disk. The simulation showed that the remnant might look like a messy, dusty spiral, what astronomers would call an SA or SPE-type galaxy.
So a merger doesn't automatically kill a galaxy. It might just remodel it. It's a rebirth as much as it is a death.
That's the perfect way to phrase it. It creates a new structure, often with a fresh population of young stars born in the chaos. But, and this is a big but that leads us right into our next section, a galaxy cannot just keep growing and forming stars forever. If it did, the universe would be blindingly bright. Something has to stop it.
The kill switches.
Yes. When you talk about quenching.
This is a concept that I think is really important to grasp. We see these galaxies forming stars, but most galaxies we see around us, the massive ones at least, they seem to have stopped. They're done. Why?
It's a matter of efficiency, or rather inefficiency. If gravity were the only thing happening, all the gas in the universe would have collapsed into stars billions of years ago. We would be living in a universe of cinders. But we aren't. Star formation is actually incredibly inefficient.
Because something pushes back against gravity.
Exactly. We call this feedback.
And we have two main culprits for this feedback.
I do. The first one is stellar feedback. So young, massive stars have strong winds, and then they explode as supernovae. They push gas away. And that works pretty well for small dwarf galaxies.
But not for the big guys.
Not for massive galaxies, the ones like the Milky Way or larger. For them, supernovae are like firecrackers trying to stop a freight train.
Yeah.
The gravity is just too intense, the gas falls back in. To stop a big galaxy, you need something stronger. You need the monster in the basement.
The supermassive black hole. Or, as the papers call it, the AGN, the active galactic nucleus.
Let's go back to that Memphis paper, J as AGN2 versus AMJODS2, because this was the core of their experiment. They wanted to prove that the black hole is the killer.
Right, so they ran two versions of the simulation. MUGGS2 was the control group. It had gravity, gas, and supernovae feedback, but no supermassive black hole feedback.
And UMGS2 was a mess. The star formation history was bursty, as they called it. It just kept spiking, wild and uncontrolled throughout the galaxy's history. It never settled down.
It never found an equilibrium.
Never. The galaxy just kept trying to make stars because nothing was powerful enough to stop the cool gas from falling in. It was a party that never ended.
But then they ran JSAGN too, the one with the black hole.
Right, and the history was completely different. It was smoother, more regulated. The black hole acts as a cosmic thermostat.
How? Does it just eat all the gas before it can form stars?
It eats some, sure, but that's not the main mechanism. The feedback is what matters. As the black hole feeds on gas, it doesn't just swallow it quietly. The accretion disk heats up and launches massive jets of radiation and particles at nearly the speed of light.
Okay.
These jets slam into the circumgalactic medium, that huge diffuse halo of gas surrounding the galaxy.
And what does that do to the gas?
It heats it up. Crucially, it keeps it hot. Star formation requires cold gas. Gas needs to be cold and dense to clump together and collapse under its own gravity. If the gas is hot, the atoms are moving too fast to ever get together.
So the black hole is basically pointing a giant blowtorch at the galaxy's food supply. It's not eating the food, it's just making it inedible.
That's a perfect analogy. The simulation showed the black hole heating the halo gas so it couldn't cool down and rain back into the galaxy's disk. It literally starves the galaxy of fuel. The paper even describes gas being physically ejected from the inner halo, which lowers the density and makes it even harder to form stars.
And the end result is quenching.
Yes. In the simulation with the black hole, star formation shuts down, or quenches, after about 10 billion years. The galaxy runs out of fuel, the young blue stars die off, and you're left with only old red stars. The galaxy becomes red and dead. The party is over.
This connects really well to the assembly classes from that lecture note source in our stack. They categorize galaxies based on how they were put together and ultimately how they died.
That's a very useful framework for thinking about this. They distinguish between fast rotators and slow rotators.
Break that down for us. What is a fast rotator?
Think of these as the survivors of the merger process. These are Class A or B galaxies. These are galaxies that might have had mergers, but they were wet or gas-rich mergers. They had enough gas left over to settle back into a disk.
So they managed to keep spinning.
Exactly. They still have some life in them, structurally speaking. They have disks, they have organization. Our Milky Way is a fast rotator.
Then the slow rotators.
These are classes E and F. These are the fossils. They formed from dry mergers collisions between galaxies that had already run out of gas or had already been quenched by their black holes.
So when they smashed together,
There wasn't enough fuel to spin up a new disk. They just puffed up. They became round, featureless blobs. They don't spin much as a coherent body. The stars just swarm around the center in random orbits like bees in a hive.
it's kind of tragic, isn't it? A dry merger is just two corpses colliding to make a bigger corpse.
In a way. But it tells us the history of the universe. When we look at a giant elliptical galaxy, a slow rotator, we're looking at the graveyard of many smaller systems. It's archaeological evidence of a violent past.
Speaking of graveyards, we need to bring this home. We need to talk about our own neighborhood. We usually assume the Milky Way is the standard template for what a galaxy should be. If we want to study galaxies, we study the one we live in. That seems logical.
It's a natural bias. It's called the
Yeah.
Copernican principle, the idea that we aren't special. We assume our sun is average, our planet is average, and our galaxy is average. But the SAGA survey, that's satellites around galactic analogs coming out of Stanford, suggests that this might be a huge mistake.
This was a big study. They looked at 101 galaxies that are similar in mass to the Milky Way. They wanted to see if our entourage of satellite galaxies is typical.
Right, so looking at the Milky Way from the inside, we have two very famous satellites. The Large and Small Magellanic Clouds, you can see them with the naked eye if you're in the southern hemisphere. They're big, bright, and very close.
And the survey found that having two satellites that big is actually pretty rare.
It is. Most galaxies our size have fewer or smaller companions. We have a surprisingly heavy entourage, or kind of a heavyweight in our local group.
Hmm.
But that's not the weirdest part.
Okay.
The weirdest part is what the small satellites are doing.
Or rather, what they aren't doing.
Exactly. In the Milky Way, almost all of our small satellite galaxies, the dwarf galaxies like Fornax or Leo II, they are quenched. They are dead. They stopped forming stars a long time ago. Only the Magellanic Clouds are still active and making stars. It's like we live in a ghost town.
But when the SAGA team looked at the other 101 galaxies,
In those systems, the small satellites are still forming stars. They are active, vibrant little galaxies. The Milky Way is the outlier. Our environment is unusually efficient at killing off our neighbors.
that sounds ominous. Why is the Milky Way such a bully? What makes us different?
It's a great mystery. It suggests that our specific environment, maybe the density of our hot gas halo, or the specific history of when these satellites fell into our gravitational well, is different. We might be an old environment compared to others.
What do you mean by old?
The SAGA team suggests that perhaps our group of galaxies formed earlier, or the satellites fell in earlier, which gave our galaxy more time to strip the gas away from them and quench their star formation.
So we are living in a galactic retirement community, while the rest of the universe is still at the nightclub.
That's one way to put it. But it's a serious wake-up call for cosmologists. We can't just take the Milky Way and say, this is how the universe works. If we build our models based on us, we might be building models based on a freak occurrence. We might be the weirdos.
Being the weirdo seems to be a theme lately, because the James Webb Space Telescope has been throwing some massive curveballs too. When those first images came back from the early universe, we're talking redshift 10 and above, everyone freaked out.
The bodybuilder crisis. I love that name for it.
Yeah. Describe what we saw, because it was genuinely shocking.
So JWST looks back in time because of the speed of light. We were looking at galaxies that existed just 300 to 500 million years after the Big Bang. That is very early. The universe should have been in its infancy. We expected to see tiny, messy little clumps of stars. Babies.
But instead,
We saw monsters. These galaxies look huge. They were incredibly bright and seemingly massive. It was like walking into a nursery and seeing a toddler bench pressing 500 pounds. It made no sense.
it was a legitimate crisis for a moment. I remember reading headlines asking if the standard model of cosmology was broken. Did gravity work differently back then? How could stars assemble that fast? It defied the hierarchical clustering model we started the show with.
It absolutely did. If you build from the bottom up, you shouldn't have giants that early. The timeline was all wrong. But as often happens in science, cooler heads prevailed. We needed more data, and new research, specifically regarding these things called little red dots, seems to have solved the mystery.
This is the study led by Katherine Charovsky and the SIRS team. They took a closer look at these bodybuilders. What did they find?
It's a classic case of mistaken identity. They didn't just look at pictures, they analyzed the light coming from these galaxies, specifically the spectrum breaking the light into its component colors. And they found that a lot of that light, sometimes most of it, wasn't coming from stars at all.
It was the black holes again, the monsters in the basement.
Exactly. These early galaxies contained rapidly feeding supermassive black holes. We call them little red dots because that's how they appear in the images, as these compact, very red sources of light. Now, as gas swirls into a black hole, into the accretion disk, it heats up due to friction and glows incredibly bright, brighter than millions of stars combined.
So astronomers were looking at this incredibly bright light from the black hole and counting it as stars.
Right. In astronomy, we often use light as a proxy for mass. Brighter galaxy equals more stars, equals more mass. But that calculation assumes all the light is starlight. Once you subtract the light from the black hole, the light from the little red dot, The actual galaxy underneath is revealed to be much, much smaller.
So the toddler isn't bench pressing 500 pounds. The toddler is just holding a really bright flashlight that's blinding us.
That is the perfect analogy. The stellar mass drops significantly, often by a factor of 10 or even 100. And suddenly, these galaxies fit back into the predictions of the Standard Model. The laws of physics are safe. We don't need to rewrite the history of gravity.
But there's a twist, right? Even after they fixed the math, these early galaxies were still surprisingly capable.
They aren't universe-breaking anymore, but they are efficient. They are forming stars about 2 times faster than our models had predicted, so they're still overachievers.
Why? If the laws of physics are the same, why was the early universe better at making stars?
The leading theory is density. The early universe was much smaller. Everything was crammed closer together. When stars formed and supernovae went off in a modern, less dense galaxy, that explosion might blow the gas way out into deep space, stopping future star formation.
Feedback, like we discussed earlier.
Right. But in the early universe, the gravity of the surroundings was more intense because everything was so dense. It was harder for that feedback to blow the gas away. The gas got trapped, recycled, and fed back into the galaxy to form more stars.
So the gas couldn't escape, it was forced to work, the factory had all its doors locked.
Exactly. So the early universe was a very efficient star factory. Not a magic factory that broke the rules, but a very, very productive one.
Man, what a journey. Let's try to synthesize this because we've covered a lot of ground. We started with the invisible scaffold of dark matter holding everything together, the ghost in the machine.
Then we watched galaxies dance and merge, tearing each other apart to build something new. The violent dance that transforms spirals into everything else. It's not a gentle process.
No. Then we saw how black holes act as the cosmic thermostats. They are the regulators. They shut down the party when things get too hot, turning galaxies red and dead.
And through all that, we found out our own Milky Way is a bit of a galaxy killer. We live in a quiet, quenched neighborhood that is not typical of the universe at large. We're the outliers.
And finally, we learned that those impossible monsters at the dawn of time were just hungry black holes masquerading as giants holding flashlights.
It really changes how you look at the night sky, doesn't it? It's not static. It's a slow-motion crash site stretched over billions of years.
It leaves me with a provocative thought, though. You mentioned the Milky Way is an outlier. Our satellites are dead. Our environment is quiet.
Yes.
Does life need a weird galaxy?
That is the big question, isn't it? That's taking the rare Earth hypothesis to a whole new level.
Right. If we lived in one of those active systems observed in the SAGA Survey, where satellite galaxies are constantly crashing in, forming stars, exploding with supernovae all the time, would the environment be stable enough for life to evolve over 4.5 billion years?
Probably not. You'd have more frequent gamma ray bursts, more cometary impacts from disturbed orbits. It would be a much more chaotic, dangerous place to live.
So maybe you need a bully galaxy. Maybe you need a galaxy that kills its neighbors and clears out the yard to provide the peace and quiet we enjoy.
It's the rare Earth hypothesis pushed to the galactic scale. Rare galaxy. It's certainly possible that our quiet, boring, quenched neighborhood is the only reason we're here to talk about it. Our weirdness might be our salvation.
And here's one more loose thread to chew on before we go. Those little red dots. If black holes were eating that voraciously, that early in the universe, just 300 million years after the Big Bang, where did the black holes come from?
Ah, the heavy seed problem. You beat me to it.
Exactly. If you build a black hole from a dead star, a stellar mass black hole, it starts small, maybe a few dozen times the mass of the sun. How does it get to be 1,000,000 or 1,000,000,000 times the mass of the sun that fast? There hasn't been enough time.
That is the next great mystery Webb needs to solve. Did they form directly from collapsing gas clouds in the early universe, bypassing the star phase entirely? We call those direct collapse black holes.
So they were born big.
They were born heavy. That's one of the leading theories we don't know yet. But the fact that they are there, bright and hungry, so early, it hints that there is still a chapter of the cosmic story right at the beginning that we haven't read yet.
Well, on that note, I'm going to go outside and look at the Pale Blue Docks neighborhood with a lot more suspicion tonight. It's a lot darker and more dramatic out there than it looks. Thanks for walking us through the cosmos.
Always a pleasure. The wild place.
And to you listening, look up. There's a lot of drama happening in the dark. See you next time.